Okay, so for the remainder of this lecture, we're going to take a look at several sorting algorithms. We want to sort data exactly because that makes searching so much easier. Unfortunately, sorting is not free, or else we would do sorting all the time. We're going to look at half a dozen different sorting algorithms. Of course, each one of these is useful. Each one of these is relatively simple so that we can explain it easily on a couple of slides. You might be asked about some of these things in interviews, so it's useful to know these basic sorting algorithms. Also, this is going to give us more practice working with algorithm analysis in terms of big O or academically big theta performance notation. Also, these different sorting algorithms give us a way of talking about the same problem, but finding different interesting solutions to these problems. It will often be the case that an algorithm you come up with for solving a problem will work fine, but it may be possible to find a much more efficient algorithm. Okay, so the first sorting algorithm we'll look at is called selection sort. For this, let's imagine that we have a bookshelf on which we have the 10-volume History of Flugelland, but the volumes are not sorted. They're in some random order, and we would like to have them in sorted order. Well, here's an idea about how to do that. What we'll do is we'll select the lowest numbered volume from this shelf containing the unsorted volumes, and we will put it on another shelf that's empty into the next available slot. So in other words, we'll find the lowest volume and we'll put that into the first slot on the other shelf. We'll find the next lowest volume and put that into the second slot on the other shelf, and so on. And we'll just repeat this until we have no unsorted volumes remaining on our original shelf. So let's imagine that these are our two shelves here on the top of slide 30. We have the unsorted volumes on shelf 1, and we're going to sort those and put these in this other shelf down here. So in step 1A, we're going to scan through all of the volumes in the unsorted shelf to identify the lowest numbered volume. We discover that volume 1 is the lowest numbered volume, and so we move that to the first position on the sorted volume shelf. So that's one iteration of our algorithm. Then in step 2A, we scan the remaining unsorted volumes and discover that 2 is the lowest numbered unsorted volume, and we put that in the second slot on the second shelf. In step 3, we identify and move volume 3 to its correct location on the second shelf, and we just keep at this recipe. So in step 4, we will identify and move volume 4, step 5, volume 5, step 6, volume 6. And eventually, when we arrive at step 10, there's only one volume remaining that's unsorted, and we move it into the final slot on the second shelf, and we're done. Now, something to notice about this selection sort approach is that once we have placed a volume in the second shelf, the volume doesn't move after that. Okay, so when we select a volume from the unsorted shelf, we're going to put that in its final sorted position in the sorted shelf. So, for our trivial little example here, we've only got 10 volumes in the History of Flugelland, but of course your real data set may have millions of values in it, and you don't want to have to rely on having another million slots of memory sitting around waiting to receive that sorted information. So what we'd like to do instead is to do what's called an in-place sort, where in effect we're only using a single shelf to sort all of our values. So our main idea was to select the lowest remaining volume and put that in the correct position. In order to avoid using two shelves, we're going to have this sub-idea here, which is to swap the selected lowest value that we found with whatever value is currently occupying the correct position for that selected value. All right, so we're going to be swapping books on one shelf rather than moving books from one shelf to another. Here's how that goes. So on slide 35, this is the same original order for our volumes. We scan through and discover that volume 1 is the lowest numbered volume. But this time, instead of moving volume 1 to a different shelf, we're just going to put volume 1 into its correct position, which is the first position, and the value that was there, 9, is going to be swapped into the place where 1 used to be. All right, so we select the 1, and then we swap the 1 with the volume that was in its location, in this case 9. Now we look at the 9 remaining unsorted volumes and discover that 2 is the lowest numbered remaining volume. So we swap 2 into its correct location, and the value 10 that used to be there is now put in place of the 2. We continue swapping values into their correct locations. Now notice, following step 2b, 3 is in the third slot. It's also the lowest remaining volume. So in effect, we just swap a 3 with itself, and now we have all the volumes correctly sorted up to the third position, 1, 2, 3. 4 is going to swap with 9, so 9 now has actually been swapped 2 times. 5 will swap with 7. 6 will swap with 8. And then 7 will swap with 10. At this point, we have sorted the first 7 volumes in the correct order, and we have 3 unsorted volumes remaining. Actually, these 3 unsorted volumes happen to be sorted already. We can see that at this point, but our algorithm is too stupid to know that, so our algorithm just keeps grinding along, and we swap 8 with itself, we swap 9 with itself, and at this point we're done. Since we only have 1 volume remaining, that volume has to be the lowest numbered remaining volume, and it's already in its correct location because there's only 1 location left. Okay, so this slightly modified version of selection sort does an in-place sort, not using any extra memory. Now, what is the big O, or academically big theta, performance of this sorting algorithm? There are really only 2 operations going on in this algorithm, apart from looping, which we'll ignore. One is that we compare values to each other. Another is that we swap 2 values with each other. And we're going to assume that on our system, comparing and swapping take roughly the same amount of time. So if we have n values to sort using selection sort, that means that in step 1, we're going to do n-1 comparisons to identify the lowest numbered remaining volume, and then we're going to do 1 swap to put that volume into the correct place. So that's a total of n operations in step 1. In step 2, we only have n-2 comparisons to do because we've already got 1 volume in its correct spot. And of course, we do have 1 swap to perform, so that's n-1 operations, and so on and so forth until we get to the last step in our algorithm, which is step n-1. Remember that we don't have to do the nth step because the nth volume is necessarily already in the correct location after step n-1. All right, so step n-1 is only got to do 1 compare and 1 swap, so that will be 2 operations. If we add up all these operations, what we see is that this is simply the sum of j going from 2 up to n of j. And that in turn we can just rewrite as the sum from j equals 1 to n of j and subtracting 1. Now, we have an analytical solution for the sum from j going to 1 to n, which is n times n plus 1 over 2. And from that, we'll subtract 1. And we can move the minus 1 part up into the numerator by changing this to n squared plus n minus 2 all over 2. Now, 1/2 here is just a constant. And the dominant part of this performance function is n squared, We've already seen, therefore, that this is going to give us an order n squared algorithm. So selection sorting works, but it's not particularly efficient. It's order n squared, and it's going to get worse and worse and worse at a fast pace as n gets larger. Doubling n increases the sort time by a factor of 4. Here's some Python code that implements the selection sort, and I will leave you to have a look at that for yourself. Our next sorting algorithm is going to be insertion sort. Let's assume again that we have our history of Flugelland, 10 volumes in some shuffled order, and we would like to get these in sorted order in place, that is, on the same shelf. Well, here's an idea. Let's just look at the positions on the shelf, one position at a time. The volume that's in the first slot, the sub-0 slot, is sorted relative to itself, okay? So here's our initial unsorted order over here at the top of slide 41. And if we just look at the first position, 9 is sorted relative to itself. So far, so good. So up to the first position, 9 is already sorted. Now, we'll keep increasing the size of the sorted left-hand slots of our shelf by 1 with each iteration. This is going to require us to compare the volume in the sub-1 slot, this is the 10, with the 9, and if necessary, move the 10 ahead of the 9. Well, looking at the first 2 slots, 10 is already greater than 9, so now the first 2 slots are sorted relative to each other. We continue this by looking at the sub-3 slot, the sub-4 slot, etc. And for each additional slot that we add, we insert that volume in the left-hand side in its correct location. So after step 2, 9 and 10 are sorted. When we move to step 3, well, 3 needs to be inserted ahead of the 10, and then also needs to be inserted ahead of the 9. So once we have inserted 3 ahead of the 10 and ahead of the 9, now the first 3 slots are sorted. In step 4, we will insert 1 into its correct location. 1 is going to be inserted ahead of the 10, ahead of the 9, ahead of the 3. And each time we do an insertion, that's going to entail shifting a value to the right. So 10 will get shifted to the right, 9 will get shifted to the right, 3 will get shifted to the right, and then 1 will be in the correct place, and so forth. We just keep adding one more volume to our sorted sequence in the left-hand slots. Okay, so step 5 inserts 7 into the correct place relative to 1, 3, 9, and 10. Step 6 inserts 8 into the correct place. At each step, the values that we have processed so far end up sorted relative to each other. We continue up through step 10, and then, of course, we're done. As far as performance analysis goes, let's assume that shifting a value takes about the same amount of time as comparing two values to each other. We need to sort n values. In step 1, we don't actually have anything to do. In step 1, we just leave the volume in slot sub-0 in its place. So we do no compares and no shifts. In step 2, we have to do one compare, and that will in turn cause us to do at most one shift. So we have a maximum number of operations of 2 in step 2. In general, for any step j, we're going to have to do at most j-1 comparisons and at most j-1 swaps. So the maximum number of operations that we'll perform during step j is going to be 2j-2. Consequently, our worst case performance is going to be the sum of j going from 1 to n of 2j-2 operations. Now here we can pull out the factor of 2, and then we're computing the sum j going from 1 to n of j minus 1, and just a little bit of algebra will convince you that that is also an order n squared sorting algorithm. Here on slide 46, we have an example implementation of insertion sort, which again I will leave for you to look at on your own. The third sorting algorithm we're going to take a look at is called bubble sort. Okay, so we have the same setup. We have our 10 volumes of history, and we want to sort those in place. The idea in bubble sort is for each slot from 0 to 8, what we're going to do is to compare the value in the sub k slot with the value in the sub k plus 1 slot. So in other words, we'll compare the sub 0 slot to the sub 1 slot. If the value in the sub k slot is greater than the value in the sub k plus 1 slot, then we'll swap those values. And then we're going to go on to the next value for k. So we'll compare the sub 1 slot to the sub 2 slot and swap if necessary. Then the sub 2 slot to the sub 3 slot and swap if necessary. Now what's going to happen by the end of our first iteration from sub 0 up to sub 8 is that the volume with the greatest value will end up bubbling up to the end of our shelf. Because we have 10 books, we're going to do this 10 times. Each time, the volume with the highest remaining number is going to bubble up to its appropriate slot at the right end. So let's see how this works. Here's our starting array of volumes. We start by comparing slot sub 0 with slot sub 1. Well, 9 is not less than 10, so we don't do a swap. Then we compare 10 with 3. 10 is greater than 3, so we swap. Then we compare 10 with 1. 10 is greater than 1, so we swap. We compare 10 with 7. 10 is greater than 7, so we swap. And you can see that as we continue swapping here, 10 is being bubbled along to the end of the shelf. All right, so in step 1, sub-steps 0 through 8, we have identified which volume has the greatest value, and we have bubbled that up to the end. Now, in step 2, we continue the same idea. We compare the sub 0 value to the sub 1 value. This time 3 is not greater than 9, so we don't swap. But 9 is greater than 1, so we swap. 9 is greater than 7, so we swap. 9 is greater than 8, so we swap. And so on. Eventually, we swap 5 and 9. 9 is not greater than 10, so we don't have a swap. All right? So for step 2, sub-steps 0 through 8, we have bubbled 9 to the end of our shelf. And this continues. In step 3, we bubble 8 to the end. In step 4, we bubble 7 to the end. After we've done 10 steps, all of the values will be in the correct place. That is, there are no swaps taking place during the 10th step, so this implies that our shelf is sorted. All right, so let's take a look at the performance of bubble sort. Well, this one is actually pretty straightforward. We're doing n iterations. That is, because we have 10 volumes, we're going through our recipe here 10 times. And in each iteration, we compare and optionally swap n minus 1 values. So if we assume that comparing and swapping take about the same amount of time, then for n iterations, we're going to do at most 2 comparisons and swaps n minus 1 times. And a little algebra will make it clear that this is an order n squared algorithm. Now, there are a couple of simple, quote, optimizations, unquote, that we can do here. First of all, we know that each time through a step, one more value will have been put in the correct place at the end of the shelf. So during iteration k, we actually can stop comparing and swapping when we get to item sub k minus 2. All right, that is considering in step 3 here, when we get up to looking at our sub 7 item, there's no point in comparing it to the sub 8 and sub 9 items because we already know that the sub 8 and sub 9 items are in their correct places. Another optimization that we can do in order to detect that sorting is complete early is we can count the number of swaps that we perform during an iteration. And if there are no swaps, then we know that we're done. If we didn't do any swaps, that means that the array is already sorted. All right, so consider, in fact, as an example, suppose that the volumes were already sorted in proper ascending order. During step 1, we would compare 1 to 2 and not swap. Then we would compare 2 to 3 and not swap, 3 to 4 and not swap, 4 to 5, 5 to 6, 6 to 7, 7 to 8, 8 to 9, 9 to 10. And during step 1, we would have done 0 swaps, so we know immediately that the volumes are sorted, and we don't have to bother going on to step 2. However, even with these, quote, optimizations, unquote, we still end up with an order n squared algorithm. Here on slide 53 is an implementation of the unoptimized bubble sort algorithm. And on slide 54, we have added our couple of so-called optimizations in which we're counting swaps, and our inner loop is stopping one step earlier as we go through each slot in our outer loop. And again, I'll leave that to you to look through.